So in this question, we are given two long parallel wires, infinitely long parallel wires, which are carrying currents of 3 amp and 3 amp each. Both of them are flowing into the page, so the direction of the current is into the page for both of the wires. The two wires are separated by a distance of 13 centimeters. And the question is, what is the magnetic field at point P, which is at 5 centimeters from the upper current and 12 centimeters from the lower current. The first thing that you can notice is that the distances of these triangles form a right triangle. You can see that 5 squared plus 12 squared is equal to 13 squared. So this is a right triangle, so this angle is 90 degrees, and that simplifies the problem by quite a bit. Well, first of all, let's recall what is the direction of the magnetic field lines for a long parallel current carrying wire. So let's say that this is a wire and the current is flowing upwards. Then we can use the right hand rule to find the direction of the current at every point, and the magnetic field lines are following the direction of the fingers of the right hand if the thumb is pointing in the direction of the current. So magnetic field lines are actually circles around that wire. In our case, the current is actually flowing into the board. So if the current is flowing into the board like that, then the direction of the magnetic field line again can be found using the right hand rule, but now the thumb is pointing into the board like that. Okay, so the magnetic field lines are going this way. So again, you draw a circle, and the direction of the field at every point will be tangential to that circle. So if, say, I want to find the magnetic field at this point, all I have to do is I draw a tangential line to this circle at that point with the direction of field pointing in this direction. So this is the direction of the magnetic field. Now, using that, we can find the direction of the magnetic field created by each of these currents at point P. So let's start with the first one. So the direction of the current is pointing into the board. Magnetic field lines are going like this. And remember, this is 90 degrees. So if I draw a circle of this radius, of 5 centimeter radius, it will look something like this. And the tangential to that circle at that point will go exactly along this line, because it's a 90-degree angle here. So this we can call is B1. A similar approach can be adopted to the second one. So the second current is going into the board, and the direction of the magnetic field at point P due to the second current would be going along this line. So this would be B2. So now let's find the magnitudes of B1 and B2. We know that magnitude of the magnetic field created by a current carrying wire B is equal to mu 0 I over 2 pi r, where r is the distance from the current, and this is for an infinitely long current carrying wire, where mu z is equal to 4 pi times 10 to minus 7. So let's calculate B1 and B2 individually. Okay, so B1 is equal to mu 0 I over 2 pi r1, where r1 is this distance, 12 centimeter. So this gives me sorry, we are doing B2 now. This is B2. If this is 12 centimeters, that's B2. So this will be 3 over 2 pi R2, which R2 is this one. This is R2 and this is R1. Okay. So R2 is 12 centimeters, so 0.12. So that is equal to 5 microtesla. And then we do the same thing for B1. So B1 would be equal to mu 0 I1 over 2 pi R1. So I1 is here, R1 is here. So that is 4 pi times 10 to minus 7 times 3 over 2 pi, and R1 is 0.05. And so you get 12 microtesla for that. So now we know the magnitudes and directions of both magnetic fields, and we need to find the total. Now, remember that this is a 90-degree angle here, so we can just use the Pythagorean theorem to calculate for the total magnetic field. So this would be the total magnetic field, B total. So B total is then equal to B1 squared plus B2 squared. B2 is 5, B1 is 12, so 5 squared plus 12 squared under the square root gives us 13, just as the sides of the triangle. So 13 microtesla is the magnitude of the magnetic field total. It may not be entirely obvious, but the direction of the total magnetic field in this particular example is actually pointing straight down. And the reason why is because the magnitude of B2 is equal to 5. The magnitude of B1 is equal to 12. So this angle is the same as this angle, because here the distance is also 5 and this distance is also 12. So these two triangles are actually similar, and this angle is equal to this angle, which is only true if this line is parallel to this line. So B2 is pointing straight down with this, and this is the magnitude of the magnetic field.